This is the fourth and final section of the elastic collisions in one dimension, and here we have successive direct impacts. So this could be something where you have like two particles here, A and B, they're moving towards each other, they impact each other like this and move off in their own directions, and then maybe, so this will be like the first collision, like this, and then what happens after that is that B then goes on to hit C. C might be maybe at rest or something like that, yeah, and this goes on to hit this one, yeah, and then this carries on that direction, so something like this, and this will be the second collision. Yeah, should be an S on the end of that one there. Right, so what have we got? We've got impulse that we can use for these types of questions. We have the conservation of linear momentum. We have loss of kinetic energy. And we also have the coefficient of restitution. Yeah, so you've got all sorts of equations that we can use, and often these equations involve like use of simultaneous equations, use of letters, algebraic answers rather than numerical ones. Okay, but the key to this has got to be drawing clear diagrams. Clear diagrams showing clearly what's going on so that you understand what's going on, and as you work things out, label them. Label your diagrams with masses, with velocities, all that type of thing. Make sure you're clear about which direction you're choosing as positive as well. Yeah, because you don't want that to cause confusion. Three spheres, A, B and C. Their masses are m, 2m and 3m. They're moving in the same straight line in a horizontal plane with A following B, which is following C. So I'm going to take this direction as positive, all moving like that way. That's how I'm going to do it. Initially, the speeds of A, B and C are 7, 3 and 1 in the direction of A, B, C. Sphere A collides with B, and then B collides with C. That's the second collision. The coefficient of restitution between A and B is a half, and coefficient of restitution between B and C is a quarter. Part A, find the velocities of the three spheres after the second collision. Right, so the first thing we're going to do is a diagram of the first collision. Right, so that first collision is going to be between A and B. So let me draw these here. So A and B, and their masses are m and 2m. They're all moving in the same straight line. A is moving at 7 and B with 3, so it sort of catches up with it. And I'm going to call the speeds of them after this first collision V1 and V2. Okay, what I'm interested in is the speed of them after the second collision, and the second collision takes place between B and C. There we go. So B and C of masses 2m and 3m. So in the second collision, B is going to be travelling at speed v2, yeah, from whatever it was after the first collision. C is going to be travelling at speed 1, and we want to find the speeds after these collisions here, which I'll call V3 and V4. Now actually, once we've found the speed of A, yeah, that will be its final speed because it doesn't collide again. But we want these two as well. So we actually want V1, V3 and V4. Okay, let me choose a positive direction. So I'm choosing this direction here as positive, and let me put the values of E for each one. So for the first one, coefficient of restitution here is a half, and for the other two it's a quarter. So the equations I'm going to be using are conservation of linear momentum and coefficient of restitution. So let's start with this first lot here, and let's do our conservation of linear momentum. So that will be the momentum before 7m before plus 3 times 2m equals, after the collision, it's going to be v1m plus 2m v2. Okay, that can be simplified, and everything can be divided by m as well. So all of these m's all cancel out, and that will give me 7 plus 6, which is 13. 13 equals v1 plus 2v2. Okay, so that's equation number 1. I'm going to highlight that because these things can be easily lost if we're not looking out for them. And then we'll do the coefficient of restitution. Coefficient of restitution, and that's going to be the speed of separation, which is going to be v2 minus v1 over the speed of approach, which is going to be, well, I know it's 4, but it's 7 minus 3, isn't it? And that equals a half. So that's going to give me, if I cross multiply, 2v2 minus 2v1 equals 4. So there's my second equation. I can solve these simultaneously quite easily. Now I've just been very lazy and got my calculator to solve these, and I've got v1 as 3, that was basically x on my calculator, and v2 as 5. Right, now what did we say? We say that A isn't involved in any further collision, so we can write down straight away that the velocity of A is 3 meters per second. That's not going to change. Okay, but we will use the 5 in the second part. So in the second part, I can take this v2 out, and let's put 5 there. Yeah, because I've just worked that out. So it's now about working out this v3 and v4. Same thing again, conservation of linear momentum, and again taking the same direction as positive. So 5 times 2m plus 1 times 3m equals 2, or v3 times by 2m plus v4 times by 3m. Just like before, all of the m's cancel out like this, and I will end up with 10 plus 3, 13, just like last time. So 13 equals 2v3 plus 3v4. 3v4. So again, like before, highlight the equation so it doesn't get lost. And now coefficient of restitution. Speed of separation is going to be v4 minus v3 over the speed of approach. Well, I can see that's 4, but I'll write down 5 minus 1. And this time that equals a quarter. Cross multiply, and I'll get 4 v4 minus 4 v3 equals 4. Everything can be divided by 4, can't it? So that'll give me v4 minus v3 equals 1. So I'll now solve these simultaneously to get v3 and to get v4. Okay, I'm being lazy again. I'll use my calculator, and I get v3 as 2 and v4 as 3. So I can write down now the velocity of B after the second collision will now be 2 meters per second, and the velocity of C will be 3 meters per second. Okay, and they're all in the direction of ABC. Now, because it says the velocities, I shouldn't just write the speed down, so I should really say what the directions are. So in the direction of A, B, C. Okay, so there are velocities after the two collisions. And part B says, explain how you can predict that there will be a further collision between A and B. Well, it's because if we look at the speed of A, it's now faster than the velocity of B, so there's going to be a further collision. And I suppose we could work out, if we wanted to, what's going to happen after that third collision. So part B, there will be a further collision since the velocity of A is greater than the velocity of B. Okay, so it's going to catch up with it, and they are moving in the same direction. So they're bound to collide. A uniform sphere of mass 3m is moving in a straight line with speed u on a smooth horizontal table. A uniform sphere q of mass m is moving with speed 2u in the same straight line as p, but in the opposite direction. They collide. The velocity of p and q after the collisions are w and v, and the coefficient of restitutions p and q, and v and w are measured in the direction of motion of p before the collision. Right, so I think it makes sense to maybe choose this direction, the motion they were moving in before, as the positive direction. So we have P, 3m, Q, m. So before the collision, they are moving in opposite directions with velocities u and 2u. After the collision, they're moving with velocities v and w. And the coefficient of restitution between them is e. So let's start with the conservation of linear momentum. So we'll have 3mu, or 3m times u, then minus 2u times m. Then after the collision, we will have 3mv plus mw. Every term has got m in it, so that will cancel out. And we'll end up with 3u minus 2u, which is u, equals 3v plus w. Okay, so equation number 1. Now the coefficient of restitution, that's going to be the speed of separation, which is going to be w minus v, over the speed of approach, which is going to be 2u plus u. So we have E equals w minus v over 3u. So here's our second equation. Right, so if we take this coefficient of restitution and we can write 3eu equals w minus v, we now want to substitute this into this equation to eliminate v and to eliminate w. Let's start by eliminating w so that we can make v the subject, or what might be easier actually is to no, let's do it that way. So I will have taken the, I call it equation number 1. So equation number 1, I'm going to rearrange it. So I get w equals u minus 3v. So I can use this equation here. If I rearrange it to make v the subject, I will have v equals w minus 3eu. Plug that into here, so I get w equals u minus 3, then w minus 3eu, w equals u minus 3w plus 9eu. So if I get this, 4w equals u plus 9eu, and then I can say w equals basically all of that over 4. So there's my expression for w. If I do the same thing and substitute in to get v as the subject, I'll get v equals u minus 3eu over 4. So you'll see you get a similar expression. So we've got our expressions for v and w in terms of E and U. Okay, part B, it says show that if the direction of motion of P is changed by the collision, then E must be greater than a third. Now if the direction of motion of P is changed, which basically means it's going to move that way, then V is going to be negative. V will be negative. Now we've got an expression for V. It means that this u minus 3eu over 4 will be negative. Okay, whoops, not negative. Negative there. Right, so let's times both sides by 4, which basically means that u minus 3eu is going to be less than 0. Right, so if we take away u from both sides, so we got this. Now if I divide both sides by u, I'll have this, negative 3e is less than, I was dividing by u, wasn't I? So that's fine because don't have to flip the sign yet because u is positive, so it's less than negative 1. Now if I divide both sides by negative 3, I do need to flip the sign. Yeah, so negative 1 divided by negative 3 gives me a third. So there we go for part B. Following the collision with P, sphere Q then collides and rebounds with a vertical wall which is perpendicular to the motion of Q. The coefficient of restitution between Q and the wall is E dash. Given that E is 5 and P and Q collide again in the subsequent motion, show that E dash is greater than a 9. Right, so let's draw a diagram of what's going on here. So if this is the wall, like this, and Q collides with the wall, so this is Q here, of mass M, so it collides with this wall, and it's going to be a velocity of W, so that's what it's going to be after that first collision, and then it rebounds back. VW, let's just call this X, the next letter in the alphabet, and that coefficient of restitution is E dash, so E dash. So starting with the coefficient of restitution, which is E dash, that's going to be the speed of rebound over the speed of approach, so that's going to be X over W. Now we know that W equals this U plus 9EU over 4, but now we know that E is 5 over 9, so we can now put U plus 9 times 5 over 9 U over 4. That will give you 6U over 4, which we can simplify down to 3U over 2. So this is what W is. So this W can now go into our E dash formula. So we can work out what X is. So X is going to be E dash times by W. So that's going to be X equals 3 E dash U over 2. So we can now update our diagram, and let me put the wall here, and we have Q and P here. We know that after Q has rebounded from the wall, its velocity is going to be 3 E dash U over 2. Now we can substitute the 5 over 9 into the velocity for P, which is going to be this one here. So if we substitute our 5 over 9 for E in here, what we get is a velocity of P which will just become U over 6. Yeah, this will just become U over 6. Let's put that down. U over 6. Now it says that they collide again. Now for them to collide again, it means that this velocity, the 3E dash U over 2, has to be greater than this velocity, so we're almost there. So for a second collision, 3E dash U over 2 needs to be greater than U over 6. We can do a little bit of cross cancelling, so that will just become 2, like that. In fact, we're not going to do that. It's not an equals that we're dealing with here. Yeah, we'll just times both sides by 2 and then times both sides by 6. So we'll have 18 E dash U is greater than 2U. Then divide both sides by U like this, then divide both sides by 18, and we will have that E dash is greater than 2 over 18, which is a ninth. So it is greater than a ninth. So I should say somewhere that since they collide, so when I wrote down this bit here, I should be also writing down something like that's true because there's a second collision, rather than just writing it down. I should state why I'm putting that statement down. Right, so on the first drop, it's dropped from 90 centimeters, 0.9 meters. We want to work out how far up it goes. So let's consider what happens on the way down when it's dropped. So it's dropped from a height of 90 centimeters. It's dropped from rest. V, we want to work out what speed it hits the ground. So A is going to be 9.8. T we don't care about. So I'm taking this downwards as positive, like this. So V squared equals U squared plus 2AS. So V squared is 0 squared plus 2 times 9.8 times 0.9. That will give us V squared equals 17.64, and we'll square root that to find V. So V is 4.2 meters per second. That's the speed at which it hits the ground. So let's do a little diagram here. So there's the ground. The ball goes down, it hits it at 4.2 meters per second, and E is 0.5, which means 0.5, speed of approach is 4.2. We want to find out what the speed of rebound is, and that will give you a speed of 2.1 meters per second. Okay, so I'll just write down speed of rebound is 2.1 meters per second. So now I know that speed of rebound. Let's consider what's going on the way up. So we want to work out the maximum height. So that means U is 0. V is going to be 2.1. U is going to be 2.1. A is going to be negative 9.8 since we're going up. Okay, we don't care about T, so that means V squared is U squared plus 2AS. So that's going to be 0 squared equals 2.1 squared plus 2 times negative 9.8 S, which means S is 2.1 squared divided by 19.6. So S will be 2.1 squared divided by 19.6, and we get 0.225. So after the first bounce, it will reach a height of 22.5 centimeters. Right, we're now going to do the same thing again to find part B, because this is now the second bounce. So on the second bounce, I suppose we could just change some of these values, couldn't we, and just use all of this working here again. Because on the second bounce, the only thing that's different is now the height. It's not 0.9 anymore. It's now 0.225. So anywhere we've got 0.9, we can put 0.225. So I'll use some of this again, like this. Save me writing it all out again. That means that this U is going to be different, isn't it? Some of this is going to be different, so let's get rid of that. Okay, so this time, as it goes down, it's coming down from a height of 22.5 centimeters. So V squared is going to be 2 times 9.8 times 0.225, which is 4.41 for V squared. So V is going to be the square root of that, which is going to be, oops, try again. 2.1 meters per second. So we're going to use E again. Speed of rebound over speed of approach, so 0.5. The speed of approach is 2.1. We want to find the speed of rebound, so that's going to be 1.05 meters per second. So that will go in for our U. So that will go into our formula. So V squared 0 squared is 1.05 squared plus 2 times negative 9.8 S. So S will equal 1.05 squared divided by 19.6. Let's work that out. 1.05 squared by 19.6. And we'll get 5.625. Sorry, I'll put 10.5 in rather than 1.05. So that should be S equals 0.05625. Okay, so after the second bounce, it rebounds to a height of 5.625 centimeters. Part C, find the total distance travelled by the ball before coming to rest. Now what happens is the ball is dropped from 90 centimeters. It bounces up, down, like this. Okay, so this is my ground here. Now the first time it drops from a height of 90 centimeters, and then it's 22.5 up and down, and then 5.65 up, 5.625 up and down. So we want to find the sum of this. So what we should notice is that each time, so 90 is the first height, 22.5 the second height, then 5.625 the third height. Each time it's a quarter of the previous height. Yeah, it's going down by a quarter. So we're going to use the sum of a geometric series to work out what's going on. We're going to assume it's just going to keep bouncing and bouncing. So we want to do 90 plus 2 lots of 22.5 because it goes up and down, plus 2 lots of 5.625 because it goes up and down, and so on. I want to keep going like that. Now we're going to do this in meters, and we're going to use this, the sum of a geometric series, which is to infinity, which is the first term over 1 minus the common ratio. Now I'm going to do this in meters. So we've got the 0.9 that we start with, then 2 lots of this thing that goes on for infinity. Now the first value is going to be this 22.5 centimeters over 1 minus the common ratio. If we work this out, we get 3 over 2, or 1.5 meters. So we're saying if it bounces forever, that's how far it will go. So when we get to part D and we want to criticize the model, well, we talked about the fact we assume there is no air resistance, but yeah, we're assuming it bounces infinitely. So infinite bounces, is that really realistic? Yeah, so some sort of comment about that would be fine for D. Okay, you should now be able to do exercise 4D on pages 89 to 91. Remember, clear diagrams, really important. Clear diagrams for each collision. So each collision should have its own clear diagram. Be careful with your equations as well, and they're going to be conservation of linear momentum and the coefficient of restitution. Yeah, they're going to be your main ones, and it's often solving these things simultaneously. And be careful where you need to work out things like this with your signs, because it needs to match up with whatever direction you've taken as positive. And don't forget to reverse the signs if you multiply both sides of an inequality or divide both sides of an inequality by a negative number.